Ew.
I think that's fine. Okay. So let's jump into it. You guys got a break yesterday. I got confused, but I sent that email saying, I'm showing up and I'm giving people quizzes. Because I didn't realize that we got suspended for weather. I thought, because I know a bunch of other colleges that took a holiday yesterday anyway, like it's been in their academic calendar. So I wasn't sure if you guys thought it was a holiday, even though it wasn't. So that's why I sent that email.
What holiday was yet?
I have no idea. But literally the entire CUNY system, for example, they had yesterday off, regardless. So I was like, do they think we have a holiday tomorrow or not? So I sent that email, I was like, yeah, we're definitely coming. And then I checked the website, oh, it's because of the weather, okay. Okay, but in the meantime, let's jump into it. Recall, last time, we solved the rate problem by developing something that we call the derivative. It didn't seem like a big deal at the time, but it is a very big deal. So we defined a function that we call f prime. And what was the definition? Yes, and you should know how to use the definition to find derivative for the quiz. Yeah, just go, tell me.
The limit as h approaches 0 of f of x plus h minus f of x over h.
Over h. Right, it was the limit of the difference quotient. The difference quotient gave us the slope of the secant line that we called it. And basically, if we turn a secant line into a tangent line by letting the distance between 2 points approach 0, that gave us what we call the derivative. And this was the slope to the curve at a specific point. This is the slope of f of x at x, or slope of tangent line at x. You can also think of it as the rate of change of f at x. That is, how fast is the y value changing with respect to the x value at x. Okay? So that was a very important definition, so you should know that by heart. Not only would you be required to actually regurgitate it every now and then, but you should actually know how to use it to find derivatives. And last time we actually used this definition to find the derivative of the x squared, y equals x squared, and find the equation of a tangent line. So now, what I want to do to start out is just to use this a bit more to find derivatives via this definition for some specific functions. Then we'll start to talk about its properties and general rules that would allow us to find derivatives a lot easier. Because finding a derivative via a limit can be quite annoying if you don't have to do it. But it's Calc 1, so you should know how to do it, but eventually you're not going to use this unless it's very much needed. But it's a very important definition, and it represents our solution to the rate problem. Turns out we can think of slope as speed. So what I want to say now is I want to use limits to find, and again, this is if it exists. So it's a limit, it's still possible for it to not exist. We'll talk about cases where it might not exist later. But for now, we're going to deal with some nice functions for which this limit does exist. Let's do some examples here. Let's say f of x is c, where c is a constant. Let f of x equals c times x. Again, c is a constant. C. We want to let f of x equals the square root of x. We're going to find what the derivative of that looks like. D. F of x equals 1 over x. I'm going to find what the derivative of that looks like. And E. Let's actually look at a trig function. Let's look at what the derivative of sine x looks like. So we're going to compute some derivatives for these particular functions using that definition. It should be something that you know how to do. And whenever you see a question that's phrased like this, you know this is what you should do. So it says use limits, or it might say something like use the definition of the derivative. Right? So whenever a problem says one of those two phrases specifically, it means it wants you to use the limit definition to actually find the derivative. If a problem does not say that, then do whatever you want. But after we go through the shortcuts, you wouldn't want to use this way if you were given the choice. So let's actually look at some of these. A. What do you think the derivative is going to be here? What would you guess the answer is? Knowing that the derivative just gives you the slope. Function y equals c is what kind of function? Yeah?
Is it 0?
It's 0. Why?
Because it's a straight line.
Because it's just a straight horizontal line. We expect the slope to be 0. Yeah.
On the quiz, if you already if you know this horizontal line, you have to put it into the.
If the question says this phrase specifically, you have to use it. Eventually you won't, but if that comes up, which it will come up, you have to use that. So here, we would say that f prime is equal to, again, I keep writing down the definition until you have it burned into your brain. What is f of x plus h for this function? No. What does f of x plus h mean? F of x plus h means you go to the function, everywhere you see an x, you replace that x with x plus h. Are there any x's here? No, so nothing changes. Remember what that means, f of x plus h. Minus f of x, well, that's the original function c over h. Well, that's just 0 over h, which is 0. So the derivative of any constant is 0. What we could do is we could take this as a general rule. So we can state as a rule, this is just something you can just know from now on, is that the derivative, we looked at this notation last time, of a constant is 0. And you can take that as just something you know now. Okay. So, for example, if I ask you, what is the derivative of 5? Well, the answer is 0. What is the derivative of pi? Or, I was going to write e to the pi. What is the derivative of pi? It's 0. What is the derivative of 17.9? It's 0. Derivative of any constant is 0. That's just... So when it comes to shortcuts, this is one of the shortcuts you will know. Derivative of constant is going to be 0. Doesn't matter what the constant is. Doesn't matter how ugly it looks. So I could ask you, what is the derivative of e to the pi squared minus radical 2 over 17.8? I can ask you that, and the answer is 0. Do not be afraid of how something looks. It's a constant, the derivative is 0, and that is a constant. Let's look at example B. What if we have a constant times x? What is that derivative? Well, again, knowing that the derivative is the slope, what do you think that should be? Yeah?
It would be x, right?
No. If you have a constant times x,
No,
like,
BC, sorry, BC.
it would be c. Like, if you have y equals 5x, what is the slope of that line? Well, it's 5. Right? So that's what we expect the answer to be. But let's actually use the definition to see this. So here, f of x equals c times x. This means that your f prime limit as h approaches 0. What is, let's write this out, f of x plus h minus f of x all over h. This is the limit. What does f of x plus h look like here? This is your f. What is f of x plus h?
C times the quantity x plus h.
C times x plus h minus cx over h. You'll realize that in the top, you can expand the parentheses. This is cx plus ch minus cx all over h. Can't cancel the h, yes, because of the sum, but cx minus cx go away, and then the h will cancel that h. And so this is just going to be the limit as h approaches 0 of c, which we know is going to be c, because there is no h here. So again, you can take that as a general rule. Derivative of a constant times x is just a constant. In particular, if c equals 1, we just get the function x itself, and we can just know from now on that the derivative of x is 1. There's some shortcut forms of that. It'll be nice to know. So again, doesn't matter what the constant is, what it looks like. This will tell you the derivative of 5x is 5. It also tells you the derivative of ex is e. So it tells you the derivative of pi minus e over radical 2 times x is pi minus e over radical 2. Derivative of a constant times x is always going to be a constant. And the things that I'm boxing are things that it'll be nice for you to just know these right away. You should probably have them memorized. Third example, let's look at problem C. If x is a radical, this means our derivative will look like the limit as h approaches 0 of x plus h minus f of x over h. What would f of x plus h look like here?
Square root of x plus h.
Square root of x plus h minus the square root of x all over h. How do we find that?
Multiply by conjugate.
Multiply and divide by the conjugate. Oh, look at you guys are quick today. God. One day of rest, huh? Like I actually got like 8 hours sleep last night. For the first time all semester. Multiply and divide by the conjugate would be the trick for something like this, which we know because we're awesome at algebra. Notice that in the numerator, this looks like the difference of squares formula, the factored form, a minus b times a plus b. So the result is going to be a squared minus b squared. And in the denominator, we would have this one. Now you'll notice that we have x minus x, and then this h will cancel with that h because there will only be an h left in the numerator. And so this will look like the limit as h approaches 0 of 1 over radical of x plus h plus radical of x. And now, if you plug in h equals 0, which unless x is 0, the denominator is not going to be 0. So we can say this is just going to be 1 over 2 radical x. So at this point, square root of x is a very common function for us to take derivatives of. Let's just make that a rule. So I know whenever I see square root of x and I want the derivative, it's 1 over 2 radical x. Of course, this is assuming your x is not 0, because otherwise we have a problem. And of course, that means also x has to be greater than 0 for the square root to even work in the first place. Or if you so choose, you could remember it as 1/2 x minus 1/2. We'll see another way to get to that pretty soon. By the next class at least. So the derivative of the square root of x is 1 over 2 radical x. Let's take a quick look at 1 over x. So remember, f of x plus h means I go to the original function, everywhere I see an x, I replace with x plus h. That will look like this. That's your f of x over h. How do you simplify that?
You do a common denominator,
Which is what here?
x times x plus h. For
So we have the LCD. So multiply and divide by the LCD. So this times that, the x plus h is cancelled, we're just left with an x. This times that, the x is cancelled, we're left with an x plus h. Be careful of the parentheses here. Rookie mistake. Over 8x times x plus h. If you have it, of course, resist the urge to cancel the x plus h. You can't do that here because it's separated by a sum. However, the x will subtract the x. And we'll have a minus h left over on the top because of the distributive law. Now the h is cancelled. And I can plug in h equals 0 in the denominator. So this will give us minus 1 over, well, it can be left over with x squared at that point. We'll take this to be another formula. It shows up often enough for us to just know what that is right off the bat, and you'll see as we move on in the semester. These are some very common functions to encounter. So we can state this as a rule: the derivative of 1 over x is minus 1 over x squared. Or say the derivative of 1 over x is minus x to the minus 2. There are times when that'll be the nicer way to see it. Let's look at sine. Again, f of x is going to be limit to h equals 0. F of x is h minus f of x. H and be the limit as h equals 0. What does f of x plus h look like here?
sine of x plus h?
Sine of x plus h. How do I deal with the sine of x plus h? Yeah?
Isn't that sine of x times the cosine of h plus the sine of h times the cosine of x?
That is right. Jeez, you are on point today. Okay, you use the addition formula for sine. That's what that would become. Sine does not distribute across a sum. So if you think this was sine x plus sine h, very wrong. There's an addition formula for sine, and that's it. There's also an addition formula for cosine. You should also have this memorized. But yes, that is the addition formula for sine. Now let's try to figure out how we can make this work. One way is to notice that we have sine in two terms here, but one of them is attached to a cosine of h. I'd still probably put those together. So I would have sine of x cosine of h minus sine of x over h, which I would probably factor out a sine here. So what we can look at is, it's that. And I'm going to separate the sine h cosine x all over h. See why I separated those pretty soon. What is the first part going to be? What is this?
0?
Yeah.
It's 0. This is a special trig limit, right? Remember cosine of x minus 1 over x as x approaches 0 is 0. So this part here is going to go to 0, so we'll have 0 times that sine x, and that's going to go away. So it's going to be 0, plus I'm actually taking the limit now, so I can remove the limit sign. What about this guy? Yeah?
Is it just cosine x?
It's just cosine x, how do you know?
Just sine h over h.
Because we have that sine h over h. As h approaches 0, that's also a special trig limit, so that's just 1. So we have 1 times cosine here. Therefore, we get cosine of x is the answer. The derivative of the sine function is the cosine function. That we can take as a rule, something you should know. We don't yet know enough to derive the, well, we can similarly, I'm just going to tell you what the answer is. I don't want to waste time deriving it. But you should do it on your own. This is a rule we can take now. And I will just say similarly, we can show that if I were to take the derivative of cosine, that will give me the negative sine function. So these are two things we know now. To be able to derive the formula for the other trig functions without having to go through this annoyance, we'll develop some other rules to do those. But for now, this is a good start to actually just know these things right off the bat. Derivative of any constant is 0. Derivative of a constant times x is going to just be the constant. In particular, derivative of x is 1. Derivative of radical x is 1 over 2 radical x. Derivative of 1 over x is minus 1 over x squared. Derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine of x. And for this verification left to the reader, good. So I went through a bunch of examples basically showing you how to use the limit definition to find the derivative of a function. You'll notice for different functions you'll have different tricks. Sometimes multiply and divide by the conjugate, find the common denominator, whatever the case may be, some algebra rule is going to help you get through that. Okay, so you have to be very careful with distributing your signs correctly, using parentheses, all that good stuff, you need to be able to compute this limit. So yeah, on the quiz, there's a problem like this. And on the first test, there'll definitely be a problem like this. And on the final, there'll definitely be a problem like this. It's valuable to us for historical reasons. Most of the time in practice, you're not going to be using this when finding derivatives. But it's still a very important thing, especially if you're going to be like a math major. From time to time, math people encounter functions for which they don't know the rule, and whenever they do that, they have to go back to the definition to try to figure it out. However, to be fair, it can be kind of annoying to be using this rule all the time, to actually go through this limit. So now we're going to start to develop some tricks that will help us to find derivatives easier when we're not required to do it by the definition. And the journey to do that starts with us figuring out some properties of the derivative, algebraically, let's say. So let's do that first. How does the derivative behave under our arithmetic operations? So the algebraic properties of the derivative. So I'm just going to derive some things for you. You don't need to know how to derive them, but I just want to show them anyway, because it's not going to take a long time. And but once I show them, you can just know it now. So let's say f of x is a differentiable function. As always, there's a technical definition for that term, but basically when we say something is differentiable, it means the limit definition of the derivative, that limit will exist whenever we try to take it. The derivative limit exists. We can find its derivative. As I said, there are functions for which we cannot find derivatives. We'll talk about those later. There are some functions where at most points we can find the derivative, but there are very specific points where we can't. So the functions for which we can find the derivative, we can do this limit definition and everything will work out algebraically. We call those differentiable functions. So let f be a differentiable function. Let c, let me use two guys here. Let f and g be differentiable functions. Let c be a constant. Okay, so one thing you want to notice is that if I were to take the derivative of this particular function, a constant times a function that I know I can find the derivative of, what would that look like? Well, we can use the definition. F of x plus h, so that's just c times f of x plus h, minus c times f of x, all over h, by the definition. Notice here, c is a common term, and we know we can factor constants outside of limits, so we can do that here. So I can factor that constant out, put it in front of the limit. I will be left with f of x plus h minus f of x over h. And this, you will notice, is the definition for the derivative of f, which we know exists. So this will equal to just c times f prime of x. And this leads us to the first property. It's called the constant factor rule. It says the derivative of a constant times a function is just the constant times the derivative of the function. It's called the constant factor rule. So it turns out that that thing with c times x is actually very similar to what will happen in general. So for example, if I wanted to find the derivative of 7 radical x, well, that's just going to be 7 times the derivative of radical x, which is going to be 7 times 1 over 2 radical x, so that's 7 over 2 radical x. So multiplying by a constant is not going to change things that much. We just leave the constant alone, differentiate the function, and multiply at the end. This is something we can do. It's called the constant factor rule. Constants factor outside of derivatives. You can factor constants out. So that's how derivatives behave under scalar multiples. If you're multiplying by a constant, the derivative is not going to care that much. It's just going to find the derivative of the variable part, and then the constant gets factored in. You can also look at something like this. If I wanted to find the derivative of a sum of functions, so I have two functions that I know the derivative exists, and I add them together. What is the derivative of the sum? Well, we can go by the definition. It's going to be limit as h approaches 0 of this function at x plus h. Just means everywhere I see an x, I'm going to replace with x plus h. So that's f of x plus h plus g of x plus h minus, open parentheses, the original function, which is the sum, f of x plus g of x over h. You'll notice that this here is minus f of x minus g of x, and I can group them. Let's take this minus f of x, put it beside the x plus h. Let's take the minus g of x, put it beside the g of x, and we will have f of x plus h minus f of x plus g of x plus h minus g of x all over h. We know that fractions distribute across this top. So where this plus sign is, I could actually break this into two fractions. We know that limits distribute across a sum. So this is like taking the limit of that plus the limit of that. We have that from the limit properties. And so what you get is f prime plus g prime, because those give you the definition. In other words, the derivative of a sum is the sum of the derivatives. The derivative operator distributes across sums. Okay? That's a good thing to know because not all things distribute across sums, remember? For example, powers don't. But the derivative does. Okay? So limits distribute across sums, and so do derivatives. This is called the summation property. So this is the property that says the derivative of a sum of functions. You can realize that this would work with the plus or minus by just running through the motions there. Is equal to the derivative of the first plus or minus the derivative of the second. Derivatives distribute across sums. So if I know how to differentiate individual functions, I know how to differentiate a sum of these functions. So for example, I can talk about what is going to be the derivative of x squared, which we saw last time, plus 1 over x. Well, that's basically going to be the derivative of x squared plus the derivative of 1 over x. And we know this from last time is 2x, and we know this is minus 1 over x squared. That would be the answer. So if I'm adding two things together, just differentiate each term separately, and that's how you differentiate the sum. Called the summation property. So those are two important things to know. we can factor constants out when taking derivatives, and if we go across a sum, we can just differentiate across the sum. You could do both at the same time, so using both is something we can do. So someone could ask you, what is the derivative of 5 over x plus x squared minus 2x? And we can simply go through one at a time. Now, this line, you don't have to write it. I'm doing it for this. You don't have to write this technically. I just want to illustrate the property being applied. But usually, it's fine to just jump from this step to that step, where you just know in your head you're differentiating each part. Put a constant. So let's say we have all sorts of constants thrown in here. So at first it might look complicated, but then we remember that derivatives distribute across sums, and we can factor constants out. So this means you can think of this as the derivative of 1 over x, where you factored out the 5, plus the derivative of x squared, when you factored out the pi, minus 2 times the derivative of x, because we factored out the minus 2. And again, you don't have to write this line. I just want you to know what's happening. So if I ask you to show your work and you omit this line, it's fine. But yeah, this is just going to be 5 times the derivative of that, so that ends up being minus 5 over x squared. It's going to be pi times the derivative of x squared, which we know the derivative of that is 2x, so this is just going to be 2 pi x. This is 2 times the derivative of x. We know the derivative of x is 1, so that's just 2, and that would be the answer. So the constant factor rule and the summation property, or some people call it the sum rule. Summation property of derivatives, or the sum rule, can help us to find derivatives of more complicated functions without going through a lot of work. And you might ask the question, what about products? Right? So if I have f of x times g of x, does the derivative distribute across that? What about quotients? So if I have f of x divided by g of x, does the derivative distribute across that? The answer is no, but stay tuned. We're not going to talk about those today. Turns out it's the derivative is kind of weird when it deals with products and quotients. Okay. So the derivative of a product is not the product of the derivatives. The derivatives of a division is not the division of the derivatives. The derivative would not distribute across these two. So here we start to see derivative is not as nice algebraically as a limit, because the limits do distribute across these things. So I have the limit of f times g, it's the same as the limit of f times the limit of g, etc. But with derivatives, it doesn't work out that way, unfortunately. It's not that easy. So right now, I just want to introduce to you another rule that's going to be very important. We're going to use it next class to derive a lot of stuff. Next class is going to be a lot. But once we get through next class, we'll have so much power to differentiate stuff. So here's a rule I'm going to introduce first. It's kind of weird to introduce first, but the way I envision teaching about derivatives, it makes sense to talk about this one first. Usually it's about the third of the special rules introduced, but I'm going to introduce it now. It's called the chain rule. So the proof for this one is a little bit subtle. You need to be very good at the epsilon delta definition of limits in order to fully understand it. Better than I'd expect a Calc 1 student to be. So we're not going to prove it, I'm just going to state it to you. The other rules we'll prove on Friday. We'll derive everything. But the chain rule, I'm just going to state it. So just take my word for it. If you care to look up the proof, you can. If you understand it, great, but you're not required to. So it's called the chain rule. Okay. So this tells us what this is. It tells us how to differentiate composite functions. Right? That's when you take one function, you plug it inside of another function. Okay? So basically the rule says the derivative, maybe I should state something. Rule. So assume f and g are differentiable. And gx is in the domain of f. Then we can differentiate the function f of g of x by doing this rule. You differentiate the outer function, leave the inside alone, then you would multiply by the derivative of the inside function. Now, it's the first time you're seeing the chain rule, it might take some getting used to. So we'll knock out a couple examples. So basically, it's the derivative of the outer function Now at first, leave the inner function alone. And then you're going to multiply by the derivative of the inner function. It's a very important rule. It's called the chain rule. Let me just show you a couple examples of how it would be applied. But we're going to use it to derive all sorts of things. So it's going to be a very useful rule for us. And really giving our derivative formulas some bite. So, for example, let's say we wanted to differentiate the sine of x squared plus radical x. So now, notice it's not just the sine of x, it's the sine of a function. So here, we can think of your f of x equals sine x is the outer function. And we can think of g of x equals x squared plus radical x as your inner function. Notice that the sine is on the outside. We have sine of something, but there's something inside the sine that's not just an x, right? So I took a whole function here and I plugged it into here, right? So the sine is the outer function, and I have an inner function of x squared plus radical x. And now we might ask the question, how would you differentiate something like that? Well, you would follow this rule. The rule says, differentiate the outside function first, leaving the inside function intact initially. Just worry about differentiating the outside, then you're going to multiply that by the derivative of the inside. So to apply that here, we would first differentiate the sine function. What would that look like? What's the derivative of sine of x?
Cosine.
So the first one, differentiating the outer function, will give us the cosine. Now at first we're going to leave the inside function alone. Then the rule says we're going to multiply by the derivative of the inside. Now we know the derivative of the inside individually. The derivative of x squared is 2x. And we know the derivative of radical x is 1 over 2 radical x. Again, because algebra is super important, you should have parentheses here. But that function would be the derivative of this function. So we'll do more of this and we'll derive some stuff, but it's very important for you to know, if I don't just have an x plugged into a function, how you deal with it is differentiate the outer function, multiply by the derivative of the inner function. And in the first step, when you're differentiating the outer function, leave the inside alone. Don't do anything with it just yet. And then afterwards, you multiply by its derivative. If it has several terms, you need that in parentheses. Okay. We'll stop there. And on Friday, we'll do all sorts of cool things. So yeah, for the quiz, know about how to find derivatives by definition, know about what it means to be continuous, what the intermediate value theorem says, how to find limits via epsilon delta. I think that's it.
Do you have the quizzes from last time?
I do. Yes. Thanks for reminding me, I always forget. And I'll do that rule where I drop. At this point, when you have the two lowest grades will be dropped when you turn this up.